with all their atoms shown. I'm on channel 41. I'm always on channel 41. Polling is open, so you're able to respond. We'll give you about 60 seconds to respond to this question.
I think I just put in an answer.
Yeah. Don't forget that your screen has to be blank in order to answer. Don't hit that channel or go button or whatever it is in the bottom left. Don't hit any button but the number from a blank screen, or else
pointing down.
it's not
Does that
working.
mean that it's going to be this confirmation? So that it would be.
Are you talking about the Diana file?
Yeah.
Okay, so
I hope that it's sealed.
okay, so it's got to be this one because they're both going in the same direction.
Okay, great.
Like that's what I think.
So see.
Just think about this.
Oh, you know what I just did? Damn it!
What? You can fix the.
Can you change your answer?
Yeah, you can change your answer.
How do you do that?
You just re-click the button that
Oh.
you want it to be. It's always the last answer.
Okay, we're going to go for about 30 seconds.
It's A and C.
Yeah, we said B and C.
I'm from Houston. I love humidity and heat.
You love what?
Humidity and heat.
Oh man.
Okay, so we're going to go with 10, 9, 8, 7,
Yeah, it does.
6, 5, 4, 3, 2, 1, and you are cut off. Here we go. The answer is 3. 78% of you recognize the stereochemistry that is required and the diene that is used, because the bridge is actually a 2-carbon bridge. So great. Good job. If you have questions about that, you can ask after class. But usually if we're at 70 or higher, I'm not going to go over the question. This is the second question. Pick the electron donating group from the list shown. So here we go. A group or groups plural. This looks funky, I realize. That's an S. I don't know why it looks so funky.
The electron donating group.
Remember, the squiggly line is just a system. This shouldn't take us that long, so we'll go in 30 seconds.
No.
No, it's not D. A doesn't resonate.
So the thing is, also,
B is not going to resonate. It's got to C.
We count down 10, 9, 8,
Because
7,
you can't do any resonance with the other ones.
5,
Yeah.
4, 3,
Unless I'm wrong.
2, 1, and we're done. Okay, the answer is actually C and D. That's the last answer. So let's just go over this one really quick.
That was just the one I was
These two
like,
are
oh,
both
it's
electron withdrawing groups. That I'm sure of. Because an electron withdrawing group is generically an atom attached that's involved in a degree of unsaturation, usually a double bond. Okay, so involved in a degree of unsaturation to an electronegative atom. Okay, so this is a ketone attached. The attached carbon is sp2 or sp hybridized, involved in a double bond to the electronegative oxygen in this case, same electronegative atom here, but it's a sulfur attached. So these are classic electron withdrawing groups from what we were talking about last class. This is a classic electron donating group from last class because the directly attached atom, which is nitrogen, has an electron pair. Remember, it doesn't have to be shown. You need to remember that it's there. This nitrogen actually has a hydrogen and an electron pair on it. Remember, nitrogen wants 3 attachments, okay? 3 bonds that are attached, and then an electron pair. So you might need to just recall that piece. But this is definitely falling into that resonance example, okay? This here is the trick on this slide to remind you that there are 2 ways that we can have induction. You can have induction through resonance, which is exactly what we talked about last class. That's directly related to sort of understanding the constitutional isomer that results from a Diels-Alder reaction. You can also have donating groups through induction, which is a through bond model, which in essence means there are some groups that through the bond donate a little bit of electron density, of which alkyl groups are one of those examples. They donate electron density inductively, okay? Now you're all okay with the inductive withdrawing of electron density by the halogens. You're all good with that, right? But you have to remember that these R groups do donate inductively. Now if I were to classify on a one-to-one, I have resonance and I have induction. One inductive, concept and one resonance concept. Resonance is going to beat them out every time. Resonance is a surefire way to donate electron density more efficiently than this alkyl group donation. So this is what I would consider a moderate electron donating group. This would consider a weak electron donating group, because this model, to create moderate or strong donating groups, would always be resonance, and this model will always be induction. So the weak models will always be the inductive models, okay, of which there's really one inductive example, and the other models will always be a resonance model. Are there questions about this? Okay, so this is going to come up more and more as we head through the aromatics chapter. Okay, so barring any questions of this, let's just review Diels-Alder from last class. I had to turn the projectors off and stuff, so we're going to get ready to really roll here. Okay, I forgot chalk again from the main lecture hall. I am going to try and get darker chalk. People have been asking for darker chalk. I will work on that. It's just hard to remember to bring the darker chalk, the bigger sidewalk chalk. But I'll try and remember for next class. I'll keep some in my backpack. So sorry about the light chalk, and thank you for the people who have told me in class or in office hours or in email. I appreciate it. All right, so last class we were talking about Diels-Alder, and we were talking about creating these bicyclic systems, right? So that is something that you should feel comfortable with. So the question is, can you identify the diene-dienophile you'll define, but could you draw one yourself? That's really the question, right? So that's something I want you to work on just a little bit. You can see that sort of the weekly quiz and the homeworks are trying to get you to see back and forth, creating the diene and the dienophile as well as creating the Diels-Alder adduct. Okay? But I did want to talk very briefly about how to name these adducts, because you should, and I think that some of you did cover this, so you should feel comfortable with this to some extent. And I sort of wanted to extend also what we know about Diels-Alder. So this will also undergo a Diels-Alder reaction. Okay, we have electron donating groups on the cyclopentadiene, right? Because the R group is an electron donating group. And we have a withdrawing group on the dienophile. In this case, the dienophile is a triple bond. Remember that we only need to use one pi bond in order to create the necessary electron flow for the Diels-Alder reaction, which means in the end of this reaction, there will still be one pi bond in the carbon unit that brings forward from the dienophile to the Diels-Alder adduct. So as this comes forward, right, I said to you that you're always going to start, the best way to really start these is to say, okay, I'm going to start by seeing that this piece, that bridge, this is what we call bridge, the language we use. This bridge sort of moves out of the way. So you see I've kind of flipped it up. There's no reason you couldn't flip it down, okay? That's just a little bit harder to draw, that's all. So it's just sort of systematic that we work with it flipped up, okay? So we move it out of the way, and we know that these are the reactive sites, the one of them being the nucleophilic site that's going to go react with the dienophile, okay? So when I come through to draw this, the first thing I do is I draw my bridged atom here like this. That is the piece, the chunk in the Diels-Alder adduct that has come from the diene, right? I need to remember that my sigma bond is what becomes my pi bond in the Diels-Alder adduct, right? And I need to remember that as I draw these new bonds, these are my new bonds, what I just drew on. I'm going to go back. I'm erasing what are the new bonds. I'm drawing what are the new bonds. This is fun, right? Erase, draw. I'm just kidding. Okay, so here we go. So my new bond will actually include still that pi bond. It looks funky from the way that I have it, but this certainly is true. And this will maintain trigonoplanar geometry. What do I have in aldehyde? So this is going to be my Diels-Alder adduct. Now, if you remember, I'm going to draw it just a little bit bigger so we can get to this thing. So I can be crazy with it for a second. Okay. So, in order order to name this, you need to remember that there are 3 paths as I move from a bridgehead carbon to bridgehead carbon. Okay? The bridge is the one that takes 3 bonds in a diagram shown. So these are what we call the bridgehead carbons. Now, these are my starting points. I'm going to start numbering my system from either one of these bridgehead carbons. I can start at either, and I'm going to have a decided way that I'm going to flow through. Okay? Now, when I number the system, I have to number it for everything I know. And that is, number it for functional group preference first, if there is a functional group preference, and then number it for infix preference, meaning an alkyne or an alkene, and finally for substituents, right? Because that is the preference for numbering in nomenclature in general, right? You all remember that, right? That there's an infix, there's substituents in front, there's an infix, and then there's a functional group, that's the suffix that's been defined. And preference is always given to the carbon that contains the functional group first, next to the carbons that contain any double or triple bonds, and finally to the substituents. So as I number here, I'm going to want to start numbering here, because I'm always going to number for the functional group here, that is the aldehyde. The aldehyde takes preference, it gets an AL ending, as opposed to the alkene that just gets an E ending. I'm not really going to go through this entire example, but I am going to number it, okay? So this is always going to go 1, 2, if I were to have this numbering scheme, okay? If I were to have this functional group at my carbon 2, meaning I was going to have this functional group off my dienophile that is creating a molecule where I would identify the priority functional group as an aldehyde. You don't know how to name aldehydes yet, so we're going to make this something else. I'm going to make it a Cl for right now. And that's going to change, it may change my numbering, actually it might not. But so here is my Cl now. That we can name, because we are able to do this one. So the question is now, what am I going to do? I'm always going to start with this, still going to start here, and I'm going to choose 2 here, because my infix takes next priority. So that would be either one of the carbons that are involved in the double bond, but I have this added influence of having the Cl off of this double bond over here, so I'm going to take that influence to get to my lowest numbering set. So as I number through, this would be 1, 2, I have to number around this path from bridgehead to bridgehead, which means this bridgehead here is going to get 4. Okay? The next path I want to go down is the next longest path. That's a requirement. There is an alkene there, so you would do that anyway. But we always go from longest path to shortest path. So it's going to be 5, 6. I have to skip over this bridgehead because they've got number 1, right? So I skip over it and I go down the last path here, which gives me a 7 up here. Okay? So the way this name goes together is it's named bicyclo because it's a bicyclic system. Okay? Wherever you start with a ring and you create these other atoms, they're all bicyclic systems. So it starts with bicyclo, this is the parent, and then there's a bracket. And there's 3 numbers in the bracket. All the numbers in the bracket are the paths that you can move down. So between bridgehead carbons. So these are my 2 bridgehead carbons. I have a 2 carbon path, I have a 2 carbon path, and I have a 1 carbon path. That's counting the number of carbons that intervene as I move systematically from bridgehead to bridgehead. I start here, I go through 1, 2 carbons before I come back to a bridgehead. I go around the next path. I go through 1, 2 carbons before I come back to a bridgehead. And finally, my last path, I have to move through 1 carbon before I get back to a bridgehead. So this is going to be 2, 2, 1, right? 2, 2, 1. And then I need to take into account how many carbons there are total, right, which is 7. So it's bicyclo 2, 2, 1, and then it's going to be hepta, and then noting the placement of the ene, so 2, 5, 2/5, diene, right? Heptadiene. And I do have a substituent, which has to come all the way before the parent, right? So this guy is going to be 2-chloro. That's my substituent, right? Bicyclo, there's no dash. Bicyclo 2,2,1, hepta 2,5-diene. Okay? Yeah.
So the 1 is always at an intersection between the rings?
Yes. A 1 has to always be one of those 2 dotted carbons. Those are our bridgeheads. So it could be bottom one or the top one. I choose based on what my best numbering strategies are, right? So it complicates numbering strategy a little bit. I don't want to spend that much time on this nomenclature. Yeah?
Can I ask a question about stereochemistry with the sp2?
So the sp2 carbon needs to maintain trigonal planar, so you do your best to show that trigonal planar geometry there, but there is no stereochemistry there per se.
As far as endo-exo?
No, there's no endo-exo because endo-exo is only relegated to when you have an sp3 center and you can actually have below or out from the ring. Okay? All right, so think about this example. I'll put a few on the weekly quiz, right, so you can think through it. And this may be a 3-point question or something on the next exam, just so you can feel comfortable naming these systems if you ever see them during your time in your life. Because, you know, we all run into these bicyclic systems every day. This is critical information, right? That's a total joke. Okay, so we're going to move on today, and we're going to be talking about aromaticity today. Okay? So there's 2 ways that we discuss aromaticity. Okay? One is to discuss aromaticity by a very rule-based system, and one is to understand aromaticity through molecular orbital theory, of which we're going to do both of them today. Okay? So as a starting point, we always start with benzene, right? So we know that benzene's aromatic. You've heard that before. Impressive. Okay. So we know that benzene is aromatic. You've heard that before, but the question is, what is it that makes benzene aromatic? Okay? You've heard that. There's evidence for that. At first, when this was first discovered, benzene was first discovered and its structure sort of elucidated, they weren't sure if there were equal bonds here or, and I don't even know if I can do it, like long, short, long, short, long, 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 short. So something like, you know, something like this, where it was, in essence, 3 double bonds. We would name this like 1,3,5 cyclohexatriene. This is a potential name if indeed there is a double bond, a single bond, a double bond, a single bond, a double bond, a single bond, right? And no resonance. This is what we get, a new name, a specific name, relegated to the fact that there are 2 resonance forms of benzene, and the 2 resonance forms in essence are saying that that electron density, the pi molecular orbital, situates itself all the way around the ring. Now that's called resonance energy. You can hear me using that term, resonance energy. Very defeatist term almost, because that's in essence saying we're giving energy to the system, right? That's the way it's sort of implied, but it's not. What it means, it's the stabilizing force behind what we see in terms of combustion. If you were to combust this molecule here, you would expect a large enthalpic value. And what you get back, you know, you can specifically assign it. I think it's actually 360 because it's 3 double bonds, so you expect to release for every mole, 360 kilojoules of energy. But what we actually release is 280 kilojoules. So there's a huge amount of energy that's actually relegated to the ability to resonate. And this feature is called aromaticity. It's actually a play from the way that they smell. If you ever smell benzene in the lab, right, it has quite an odor to it. They would call that aromatic. Right? The odor is aromatic, we have smell to it. And that's sort of where the sort of nomenclature has been derived from. So we knew from its heat of hydrogenation how much energy is released when you add hydrogen all the way back to cyclohexane. We know that benzene's more stable than what can be assumed as 1,3,5 cyclohexatriene. So the question is, what is it that makes these systems so stable? So there's 4 rules that are sort of identified when you look across a whole bunch of aromatic systems. And we're going to assign those rules, and then we're going to look at the molecular orbital theory and sort of understand those rules as well, of what is so stable about this. So the basic rule-based system is as follows. Aromatic systems share these 4 properties. One is they're cyclic, okay? So that means they have to be in a ring. There are no straight chain aromatic systems. They have to be in a ring. We call that cyclic. Okay? The next is that these structures have to be planar. Okay? In order to have the electrons run from p orbital to p orbital to p orbital to p orbital, they have to be in the same plane. Okay? If any of them are tilted out of the plane, the electrons can't move. Okay? They have to be in the same plane. So that's like along the x-axis, right, or along the y-axis. No displacement, no angular displacement, or the p orbitals cannot overlap and the electrons cannot move. Now this is the hardest one to do because whether or not a molecule, a cyclic molecule, is planar is hard to discern. Obviously a 3-carbon ring is planar, right? A 4-carbon ring, generally planar. 5-carbon ring, planar. Even when you get to 6, benzene, still planar. But when you get to 8, 9, those can adopt non-planar geometries. As a matter of fact, it might be a little hard to maintain planar geometries. So this is something that needs to be told to you. You can obviously discern if whether the system is cyclic, but it'd be a little bit harder to discern if the system is planar, okay? So sometimes logic has to prevail, but if you have any question about it, you can ask on a test or you can ask us on a homework, and we'll certainly either say you should know that, use logic, or we'll be like, oops, we should have said it's planar, we'll put that on the board, or we'll tell the class in general, okay? That one's a little bit hard to discern, because you'd be surprised what systems are planar and what systems are not. Okay, so the next one is that there has to be a p orbital on every atom in the ring. Another way to say this is that it has to be sp2 hybridized for every atom in the ring. Okay, because sp2 hybridization comes with a p orbital that's unhybridized. Every sp2 hybridized atom comes with an unhybridized p orbital for its 4th bond, right? So that's classic, but there has to be a p orbital on every atom in the ring. And last but not least, the rule that nobody likes, which is actually the main rule, we call it Huckel's rule, okay, is that there have to be 4n plus 2 pi electrons, okay, where n is any integer. I believe from years past that 0 is an integer, but I don't know that for sure. So I think it is though. Does anyone know? Okay, very good. So that works out. So 0, 1, 2, 3. Now what you have to do when you think about this 4n plus 2 is consider it like a function table. Do y'all remember function tables from like math in elementary school, where you were given a formula and you were asked to plug in x of all sorts of varieties and get out an output, right? Like y equals 4x plus 3. We're here 4n plus 2. So the question is, what are the allowed pi electron numbers, right? So we're at, what are the allowed pi electron numbers? We know that's relegated to 4n plus 2. And when n is 0, the number of pi electrons allowed for an aromatic system is 2. When n is 1 in for n is 4 plus 2, or 6. When n is 2, 8 plus 2 is 10. When n is 3, in for 12, we have 14. And you can keep going. You can make a very extensive function table out to n infinity, right? And calculate what your pi electron allowed numbers are. If the pi electrons counted in your system do not fall into this table, they are not following Huckel's rule. So if I had 3 pi electrons, I don't know how you really get that, but let's just say, some radicals have that actually. 3 pi electrons, the answer would be no, right? 8 pi electrons. No, right? 18 pi electrons. Yes. Okay, so you have to literally be able to just draw a function table or write a function table really quickly. Maybe you don't need to write it out. You could just do it in your mind, right? And discern whether it's following this 4n plus 2 rule, okay? It's a little bit tricky to teach because everybody has a little bit of trouble with the 4n plus 2. So I'm hoping this function table concept works for this. Yeah?
N stand for number of carbons?
No, n stands for any integer. That's the thing. It's just like any n value. 0, as long as you move in whole number increments. So 0, 1, 2, and integers are indeed whole number increments, right? You can't have a fraction inch C. I'm learning, and I'm only learning from 6th grade math, I have to tell you. I would not have remembered that if I didn't just help you do this 2 weeks ago. Okay, are there questions about these rules? Okay, so we're going to discern these rules here for the systems we're going to look at. But before we do that, I want to now announce, right, benzene follows every one of these rules. Am I right? Okay, that's good. We know that. Now let's look at the MO theory of benzene. To get at the molecular orbitals of benzene, you'd be happy to know there's a schematic way to do it. Okay, and the schematic way is called cross circle. Okay, that's the schematic way that we're going to use. So if you want to look this up, this is what you're looking up. Cross circle. This is a methodology to discern the energetics of the molecular orbitals in the pi bonding system of any aromatic compound. Again, it is the methodology used to discern the energetics of the molecular is that you draw your shape, this is a hexagon, with an apex. Is that what that's called? That I haven't learned in 6th grade math yet. What is this point called? Apex? Anyone point? Does everyone know what I mean? Yeah, okay. Has to be down. I cannot draw it like this, right? Because this doesn't have apex down toward the bottom of the page. This is a no, this is a yes. Okay, so one of the points of the shape has to be directly down to the bottom of the page. Now, I'm no good really at like being very, very precise when I do this, which is trouble. But the next step is to enclose this shape in a circle. Okay, so I'm going to draw a circle around this. And truthfully, every point of your shape should touch the edge of the circle if you're being absolutely precise about it. We don't necessarily have to be that precise. The concept then is that you take half the circle and you shade it. Okay, so that's about half, right? And I shade it. You can shade the top half or the bottom half, it doesn't matter. Okay? These are the steps that you take. This is it. This is the end of the frost circle. Now I'm going to read out what the energetics are of my orbital system. So here we go. For every point in my shape, that's a representation along that horizontal displacement of the energy of that orbital, which means I have 1 point, 1 point down here means 1 orbital at this point. You see how that's just along its horizontal axis. I just read that out, 1 point there. The next place is that I have 2 points that are on the same horizontal plane, right? So I have to put 2 orbitals here. They would be degenerate, right? I've actually displaced them a little bit. I didn't mean to do that. But so there are 2 orbitals right here, okay, for each of the points. So this point led to this orbital here. These 2 points that are at the same horizontal placement read out to these 2 orbitals here. Every point in the shape, every apex, reads out to a molecular orbital. Okay? I have 2 up here, and I have 1 here. Okay? Everything in my shaded half, or the bottom half, doesn't matter if it's the shaded half or the non-shaded half, but each half represents my dividing line between bonding and anti-bonding. Okay? So this is my dividing line between bonding and anti-bonding. Now, there's a very precise way to sort of, and you can imagine there has to be, there's a very precise way of discussing these, but the whole psi system still holds. This is obviously psi 1, and this is psi 6. Whether or not you do psi 2 or psi 3, or psi 3 and psi 2, that doesn't matter, okay? Because they're degenerate, okay? And then you have psi 4 and psi 5, okay? So the question comes, how many pi electrons do I have to fill into this system? 6, because I have 3 double bonds, right? So 6 total pi electrons in my system. So in this case now, when I fill 6 electrons, I go 1, 2, that's okay. 3 goes here, you go into psi 3 as well. So 3, where does the 4th one go? Psi 3. And then 5, 6. You see you fill them all into the bonding molecular orbitals. Does everyone see that? None of them are going to hit the anti-bonding molecular orbitals. In an aromatic system, they should all fall, none of them should fall, I should say, into the anti-bonding molecular orbitals. Another no-no is one, and I don't know if I'll be able to get the example right off the top of my head in class, but I know that we can get it for next class, because it slipped my mind. You can never have something that has single electrons in degenerate orbitals. That's, if you stop at that point in time and you have single electrons in bonding orbitals, that's not allowed either, okay? You've got to have fully filled bonding orbital system, okay? So let's look at these pictures, which you'll never be able to discern, but you should be able to interpret, okay? So these pictures for psi 1, psi 2, psi 3 look as follows, okay? And it will explain. We put up psi 4 as well. This is going to take me a minute because I have to do it from my head. So let's look at these. So if I look at psi 1, that one's pretty obvious. All my p orbitals will allow for full reign of my electrons here. So they'd all be shaded above the ring here. And so I have free reign, right, of my electrons across. Okay? Side 2 and side 3 should each have one node. So there's two ways to get nodes there. So this is one way to get nodes, is to have an official node as you feel comfortable with. So my node runs right through here. The second way to get my node is to use non-bonding orbitals. People don't like that. So this in essence is saying that my orbitals here don't form pi bonds. They actually are out of sync. They're along the x displacement instead of the y displacement, which means they can't function as pi bonds. This is what we call non-bonding. The p orbitals still exist, but they can't ever be involved in bonding. But they're not anti-bonding. They're just not able. They're not capable of bonding because of their displacement, their sort of physicality in space. So this is side 3. These are the bonding molecular orbitals. If you look at side 4, so this one's with this where the double comes, because I need two nodes. So how can I do that? I think this is one way to do that. Yeah. So that'd be one node, two nodes. That's right. Okay. So, these pictures again will be drawn for you, but I do this because everything comes back to molecular orbital theory. And you can really buy into the theory here when you see these. These are born out of the mathematical analysis in this pi bonding system of an aromatic compound. I mean, that's an amazing feat to undergo, right? And to understand why some of these are bonding and why some of them are antibonding, and to appreciate the fact that they all fall into these bonding orbitals and what that means really gives you a great appreciation for the aromatic nature of compounds. So what I'm going to do here is I'm going to count the number of bonding interactions and the number of anti-bonding interactions. Okay? And I'm going to label them as B or A. B for bonding, A for antibonding. So clearly here I have 6 bonding interactions. These are all Bs, right? Bonding, 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 bonding. They're all bonding. I have no anti-bonding interactions in Psi 1. Psi 1 should never have any anti-bonding interactions. We saw that even in our straight chain conjugated systems, and that is true. That there'll always be full overlap, and I shouldn't have to worry about the presence of any node. Okay? So I have 6 bonding interactions. Psi 2 has 4 bonding interactions. So I have bonding, 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 and 2 anti-bonding interactions. So if I have 4 bonding, so here was 6 bonding, minus 2 anti-bonding, this leads to still 2 bonding interactions, right? 2 left. 4 of them are bonding, 2 of them are antibonding, and if I compare, cancel for every antibonding, I cancel a bonding, I'm going to be left with 2 overall bonding interactions. Okay? If I look at side 3, I have 2 bonding interactions, and I have no anti-bonding interactions, 0. I only have 2 bonding interactions. So this leads me to 2 bonding interactions, hence their degeneracy, because they each have 2 bonding interactions. And when I come up to side 4, which is one of the degenerate, side 4, side 5, I get 2 anti-bonding interactions and no bonding interactions, right? So I'm at 2 anti-bonding interactions. I don't have a single bonding interaction that is going to help maintain the stability of the system. Okay? So this is the dividing line, right? It's the turning line that explains to us why these 3 orbitals bring such power to the system. And we understand that filling this system will actually lend itself to the highest level of stability. Let's pause on a reflection of benzene. Isn't this amazing? We all look kind of angry, but it is amazing. Yeah. Yep, there is a homolumo gap, absolutely. And my homolumo gap would be right here. And when you actually do probe, and this is probably more classically what you do, because these aromatic systems abound in like DNA and proteins, and I'm sure you've all in biology at some point taken protein, right, to the cuvette and measured its absorbance so you can figure out how much is there. Or DNA, right? Yep. Okay, so you're probing exactly this. You're probing the HOMO-LUMO gap in these aromatic systems, right? In the proteins, it's tyrosine, tryptophan, and yeah, it's mostly tyrosine. There's another, cysteine, and that makes no sense, so don't go there. But so tyrosine and tryptophan are the main ones that actually lend themselves to absorbances at 280, which is how you can do the measurement. And that is the HOMO-LUMO gap. Okay? Is there another question back there? Yeah. No, it's not. So that requires a lot of advance. So the question is Psi 3 and Psi 2, why are they the same in stability? Why are they degenerate? The simplest explanation, right, is to count the number of bonding and antibonding, right, and do some sort of ratio. But the concept of non-bonding seems destabilizing, right, but it's actually not. So you have to learn a little bit more about non-bonding interactions to appreciate more the degeneracy here. But the simplistic way to do it is always to count up the number of bonding and subtract the number of antibonding. Yes?
I'm confused about, for Psi 3, for example, when you have the two bonding, the overlap, does the overlap signify a pi bond that's being created?
Yes. The question on the table is, if I see a bonding interaction, what does that mean? And that means that a bond, right, can exist there. So in essence, this means that I have one electron in this carbon, right, that had a p orbital, and one here, and they overlap to give me a pi bond. And I do that here again, right, but over here, these electrons are out of phase, they're out of sync physicality-wise, right, and so they don't discern any electron density overlap, so no pi bond.
So then doesn't that not form 3 pi bonds in the structure?
I know. So you're kind of like localizing electron density, for sure. You know, the idea is how much you really cut off things from the world, right? I mean, if we go to an analogy, I don't know what the analogy would be. Let's think of like a jail cell, I don't know. You know, if you're like in a row of a bunch of people, right, you all share the same jail cell, maybe there's some camaraderie there, right? You know, like when you go initially into lockup. You know, like you see on the sitcoms, right? Everyone goes into that in there. But then, when you actually are in jail, right, you're all in your own cell and you're sort of separated, but some of it is actually solitary confinement, right? So, you know, you're really working from like a holding room area to like the jail cell concept to like solitary confinement. Like this is not something, you know, that's even stable in any way. And that's why it's supposed to play on you like crazy, right? That's right. I just talked about solitary confinement. You'll not find this out of another organic professor. I am amusing myself even. Okay, so let us erase the board and talk about other systems that potentially are aromatic or not aromatic. We're going to work back to our rule-based system here for a little while, just to make sure that we can get the concept and to see some things that you might not consider aromatic or non-aromatic. Okay. Okay.
I'm just going to do the post-lab. I did like the first question and then the second question I think already.
Okay, let's work from these. We're going to say all these systems are planar, so that takes rule 2. You can see that all these systems are cyclic, right? So we don't need to necessarily worry about that. I'm actually going to add one more out here. So we can see that all these systems are cyclic. Take this guy. So planar, they're all cyclic, so we're good. So the question is, what happens with the other rules? Now, one thing that we have trouble with the rules is that we must always consider resonance. Okay? So that is going to lead to some trouble. All right? So I chose these examples specifically to sort of get at that. All right? So let's start with examples that may indeed have resonance. certainly these have resonance, but these just simply reorganize what I already see in this contributing structure. This contributing structure has 2 pi bonds and a carbocation center. No matter what I resonate, I'm always going to wind up with 2 pi bonds and a carbocation center. So I don't even need to look at the resonance here because all the pictures are going to look the same, okay? This here, though, does require a little bit of thought on resonance. The question is, where is that electron pair housed, okay? That electron pair is not housed in an sp3 orbital, which is what you might think, okay? That electron pair can actually resonate throughout the structure. Now, I'm not going to break any rules of resonance when I say, look for an electron pair, here it is, try and move it to become a pi bond to its neighboring atom. That's what I'm doing. I move counterclockwise, you can move clockwise and get the same result, okay? Knowing that that neighboring atom can accept that pi bond because it's sp2 hybridized, right? The requirement is that the accepting atom be sp2 or sp hybridized. And then to say, okay, that carbon can't take 5 bonds, so I need to give up a bond. So I give up a bond up onto its furthest carbon atom. And this is one resonance structure of many. This electron pair can move all around the ring, and what you get as resonance hybrid is the actual showing, right, that this electron pair can move everywhere and that every atom in the structure can take on a negative charge. So you can work through to that. But regardless of what happens in the resonance hybrid, you must must believe that this electron pair here does not exist in an sp3 orbital, but rather exists in the p orbital system, right? So this system here has 6 pi electrons. 2 of them are clearly the double bonds that are clearly shown in the contributing structure on the board. But the last 2 pi electrons come from the fact that if this electron pair can resonate, it is part of the pi system, okay? The minute you answer the question, yes, I can draw a resonance structure where this electron pair can become a pi bond, it is part of the pi bonding system. So now I have 2, 4, and then 2 from this electron pair, a total of 6 pi electrons in this system, okay? Does everyone understand that? Okay, great. This here is a place where there is no alternative resonance structure. Now, people have a hard time with this. People say, okay, I understand why this isn't going to move this way. That one's a little bit easier, right? Because I don't have a pi bond I can give away, right? That carbon atom would have to keep 5 bonds, and we know that it won't. So most people are okay with it resonating, the inability for it to resonate in a counterclockwise method according to my diagram. But it will not resonate in a clockwise direction either, even though the neighboring atom is sp2 and can give up a pi electron. And the reason for this no, right, because this is a no for one specific reason, this is a no because it can't have 5 bonds. This is a no because that nitrogen would then become sp hybridized, right? And an sp hybridized system is an extremely unstable system. It is a 180-degree bond angle, right, that would need to be maintained, and you cannot maintain a 180-degree bond angle in a ring structure. It is not a possibility, okay? The actual bond angle way defies the 180 necessary to maintain that sp hybridization. So we're a no on this electron pair being able to resonate, which makes this electron pair here in an sp2 orbital, okay? This electron pair here that I'm pointing to right now is in an sp2 orbital. It is not part of the pi system. Because we can resonate here, this electron pair, and some of you need better glasses, because some of you are like, so some of you definitely need glasses. Go look into that. This here electron pair is part of the p orbital system because it can resonate. This electron pair here in this molecule, a different molecule, is in an sp2 orbital because it cannot resonate. Okay? So that discernment needs to be made example to example. So in total, how many pi electrons there are in pyridine here?
6.
6. So there are 6 pi electrons. Great. system, what do we get?
4.
4. And we counted our last two systems here. How many here? Oh, we can do this. How many here? 6. Okay? Only one resonance, one electron pair will resonate. One electron pair will resonate here. And that means that only one of these is part of the system. Okay? Now, diagrammatically, pay attention, because this actually could really help, and I think it could help even on an MCAT, because they do ask these questions on an MCAT. In these cyclic systems, heteroatom, right, is nitrogen, oxygen, those are your typical heteroatoms, those columns, although sometimes we can extend it to chlorine, bromine, etc. But these are typical heteroatoms, nitrogen and oxygen. If the electron pair is outside of the ring, it isn't part of the system, and when it's inside the ring, it is part of the system. Diagrammatically, it works. Okay? So if an electron pair is outside of the system in a heterocyclic system, it is not part of the p orbital system, whereas when it's inside, it is. Okay? Generally what we see. Okay? So this has how many electrons then? This one here? 6. And how many electrons in my last one here? 2. Okay. So we have a game on the board a little bit. Okay? The game on the board is to identify the aromatic compounds and then to try and discern what we want to say about the other compounds that are not aromatic. So, which compounds on the board here are aromatic and which ones wouldn't be? 2, 3, and 4. Okay, great. These are my aromatic systems. Yes, 2, 3, and 4. Okay? Those are my aromatic systems. They follow all the rules. They're cyclic. They're planar. They have a p orbital on every atom. Each atom's sp2. And they have 4n plus 2 pi electrons. We can say something about the first and the last. The first is a very bad system. This is a system we would call anti-aromatic. Anti-aromatic and aromatic are discerned by the last rule alone. An aromatic system and an anti-aromatic system only are different from the last rule. The last rule in an anti-aromatic system is that it has 4n pi electrons. 4n pi electrons. And this system does have 4n pi electrons. Make a function table. Okay? This has 4n pi electrons. That is a function table representing anti-aromaticity. You can look at that from molecular orbital theory and see why that is the case. Okay? That's really bad and really unstable. It can't happen. Which in essence means, follow me here with a functional example here, if I took this compound and I tried to do SN1, holy moly, no way on God's green earth will that go. Because the carbocation it forms is anti-aromatic. Bad. Okay? So that's the worst. These are the best. And this is somewhere in the middle. We call this just not aromatic. Okay? And the reason it's just not aromatic is because it breaks rules, one of the rules 1 through 3. Which rule did it break? 1, 2, or 3? 3. And if it breaks one of those generic rules, rule 1, 2, 3, it can't be aromatic and it can't be anti-aromatic, so we call it just not aromatic.